Hi everybody, my name is Simon, and as one of this year's Summer of HPC students, I've been working on the project Optimal Deflation in the Linear Solver for LQCD in the LQCD group at Castor C in Cyprus. And in this video I will give you a short presentation of some of the work that I've done. Let me start out with a short introduction. First of all, what is QCD? QCD, short for quantum chromodynamics, is the physical theory of the strong interaction, one of the four fundamental interactions in nature. It basically tells us how quarks and gluons behave and how they interact with each other. Unfortunately, the theory is too complex to get analytical solutions from it, and this is why we need LQCD. LQCD is a computational framework that tells us how to compute physical quantities from the equations of QCD. This is done by considering only a finite number of equally spaced points in space and time that form a four-dimensional lattice. On this lattice we then have the quarks that live on the lattice sides and the gluons that live on the links between those sides. You may imagine it looking something like this, with the balls representing the quarks that live on the lattice sides and the wiggly lines representing the gluons living on the links between those sides. The computationally most demanding operation that we have to perform in LQCD is the solution of a very large linear system of equations of the form dx equals b, where d is a discretized form of the Dirac operator, which is basically a sparse square matrix of size 12 times the number of sides on our lattice. Since lattice sides of up to and more than 10 million sides are actually quite common, we are dealing with really large systems here, and solving them requires a considerable amount of computing power. One method to speed up the solution of such linear systems is called deflation and uses eigenvectors of the Dirac operator to accelerate the convergence of the algorithm used to solve the linear system. Of course, in order to apply this technique, we first of all have to compute the eigenvectors, which is the actual topic of the first part of my Summer of HPC project. The method that we use to compute those eigenvectors is called the implicitly restarted Arnoldi method. It is based on the computation of a so-called partial Schur decomposition. The crucial point here is that for the computation of the eigenvectors, we only need to know how the Dirac operator acts on the vector x, and all other operations needed for the computation of the Schur decomposition are actually performed on a much smaller subspace of dimension k, which is just the number of eigenvectors that we want to compute. The starting point for my project was a hybrid implementation of the implicitly restarted Arnoldi method, where the matrices D and V were split up column-wise over the compute nodes. On each node then, the action of the corresponding part of the Dirac operator on the corresponding part of the vector x was then computed on the node's GPU, while all other operations were running in serial and on only one of the node's multiple CPU cores. My task was therefore to parallelize these operations in order to avoid the waste of computational resources here. To this end, we explored two different approaches. The first one was to simply recompile the program and link it to a thread parallel linear algebra library, which of course is the simplest and fastest way to achieve parallelism here. The second approach was to go into the code directly and parallelize it manually. This was done by splitting up the matrix V that was already split up over the compute nodes even further over the multiple cores of each node's CPU, as is illustrated in the right-hand side of this figure. To test the two approaches, we performed several benchmarks. This one was performed on Prometheus, which is a local development machine with a total of 12 CPU cores on each node. Here we were able to obtain considerable speedups of almost a factor of 4, and the manually parallelized version has a clear advantage over the version using multi-threaded linear algebra. On PITS-Daint, which is a hybrid cluster machine located at CSCS in Lugano, we were unfortunately not able to obtain similarly good results. Here the speedup achieved was only slightly better than a factor of 2, and also the advantage of the manually parallelized version is almost gone. So summarizing, we can say that we were able to achieve considerable speedups from both approaches, but with increasing matrix size, the advantage of the manually parallelized version actually becomes marginal, and using a multi-threaded linear algebra library is generally sufficient. So this is what I've done in the first part of my Summer of HPC project. I hope I was able to give you an idea of what I've done so far, and I thank you for your attention.